in this class, because again, our exam will be online, right? But like I said, I'm not going to be able to give you that warning for other classes, and other instructors might not give you that warning. So, I just want you to know that now so you don't get burned on it, because that's a really crappy place to catch an academic offense, right? Okay, so this is a pretty computational question. For assignment 4. So Agam, you don't even need to show that it's true. You just, if you can come up with the matrix, we're happy. I mean, you know what? Yeah, if you can show it for one example and say from this is how it would hold for arbitrary I and j, I would be super happy with that. I think that'd be great. Yeah, don't show it for every single one. We don't want you sitting there spending 2 hours writing out all of the possible examples and showing that they work. Tell us what the matrix is, maybe give us an example to show that it works, and then say this works for all the other ones as well. Yeah, perfect. That's perfect then. Yeah, just do it like that. All right, so a bit of a computational question today as we try and figure out what the determinant of this matrix is. And determinants are not fun to calculate. This is definitely the sort of thing that we're very happy to have Octave for. Yeah, exactly. Well, because again, for those of you who, if you think about a determinant, when you compute a 5x5 determinant, what do you have to do? Well, you have to compute all the 4x4 subdeterminants, right? And then each of those 4x4 determinants also requires 3 determinants, or a 3x3 determinant, multiple 3x3 determinants. Each of those 3x3 determinants have multiple 2x2 determinants. So generally, even for a 3x3, there's potentially, 6 determinants that you have to actually calculate, right, in order to do this. And actually, it can get quite computationally intensive. Are we allowed to use Octave? Yes. Yeah, absolutely. Yeah. Now, in practice, there is actually a faster way of computing determinants, but I'm not going to show it to you just because, we're not going to use it in general. But in practice, there is actually a way that instead of taking n factorial steps, only takes about n squared steps. So generally, that's significantly smaller, right? So if you're working in a 10 by 10 matrix, n factorial is about 1,000,000 and n squared is about 100, right? So n squared steps is definitely the better one. What's the Saris rule? I'm not familiar with that name.
Saris Rule?
Yeah, I've never heard that. Alan, is that a thing?
Is it like the rule of thumb or something? I'm not sure.
Here, maybe it's just I've never heard.
I've never heard it either, to be honest.
Oh, you know what? No, okay, sure. I've seen this before. This is, I think this only works for a 3x3. I would say that, Alan, this is the sort of rule that is kind of like a nice little trick if you are only doing 3x3 matrices, but you can imagine I could give you a 4x4 or a 5x5. In fact, in a second, I'm going to give you a 5x5 that isn't too hard, but it's kind of not worth knowing these sort of one-off trick rules. It's better just to understand how you actually can compute a determinant, because again, if I don't give you 3x3, I don't think that rule works, right? So Connie, I think you have a sign wrong. I think you want a plus to be a minus somewhere in there. All right, so Connie, what row? It looks like you went over column 1. Is that what you did? Is that fair? So did you go over column 1? Or did you go, which row or column did you expand along? Okay, sure. So your 10 should be minus 10, right? Because it's 2 times that matrix in the top right, but that, right, it's going to be 5 times 0 minus 5 times 1. So you're going to get 2 times minus 5. So you should have minus 10 instead of plus 10. Yeah. Do you see it? Do you see it? Yeah. Yeah, that's what I'm saying. It's just a sign error. Yeah. Because of the minus 5. Yeah. Okay. Yeah, I've lost track of the poll question because I had to change the window. All right, so we're at about 2/3 answered. I'm very happy with the answer. Maybe people plugged it into Octave, though. I don't know. But I'm going to close it in about 30 seconds here, so get your answers in. Oh, for sure. I'm gonna do it. I'm gonna do it by hand for you. So no, on a test, if I ask you this question on a test, you 100% can just say, arrow by Octave, or I plugged this into Octave and I got, this number. And that's totally fine. But that being said, you can imagine I can make it so you have to compute it by hand, right? Like, what if I turned a couple of those numbers into variables and suddenly, Octave's not going to do it. So for that sort of thing, yeah, you kind of have to do it by hand, right? So it's still worth knowing how to do. Okay, so overwhelmingly, the class answered B. B is 35. Absolutely, that is correct. Yeah, Brandon, you could do it that way if you want. It certainly doesn't hurt. And especially if you have a 24-hour test, you kind of have the time to do that. But that being said, like I said, you can put your faith in the computer. That's okay. As long as you, double check that you entered all the numbers incorrectly, that's totally fine. All right, so here's question 2. Let's just do it by hand. And in fact, we could do it a couple of different ways, but let me rewrite out the matrix for us so that we have it in front of us. So it's 3, 5, 1, 0, 5, 0, and 2, 2, 3. Okay, now we are allowed to expand along any row or column. And generally what you should do, well, you tell me, which row or column do you want to expand along? What's the easiest one if I asked you to do it? Because you're allowed to do any of them. Yeah, the one that has the most zeros. So in this case, row 2, right? Now you don't have to do row 2 if you don't want to. You can do any of them that you want, but I think we agree row 2 has the most zeros, and so that's going to be the easiest, right? So what we're going to do, so the determinant of M, let's remember how this goes. So I'm going to expand, maybe let me use a different color for this. I'm going to write it all out. Even though there are a bunch of zeros, I'm going to write it all out. And Ahmed, absolutely, we could do column 1 or column 3. Those ones only have 1 0 though. Row 2 is actually a little bit better just because it has like 2 zeros in it, right? But you're absolutely right. Those ones would be the next choices afterwards. So I'm going to start here. And when I do that, right, I'm going to take 0 times, don't forget this part, -1 to what power? What power do I put here? What's the power of the -1? Exactly, yeah. 1 plus 2, or let me actually do it as 2 plus 1, just because that's the row and column, right? So it's row 2, column 1, and so that's what I'm going to put there. And then I'm going to like cross these out, and then I'm going to take the determinant of 5, 1, 2, 3, right? Okay. Everyone's okay with what happened there? Are there any questions? Do I need to go over that a little bit more? That's okay. Why -1? So the formula says that you always just have to put that -1 in all the time. And the reason for that, I mean, there's a complicated math reason, but you always have to have that -1 to the power of what element you're in. That just unfortunately always has to be there. Oh, so you multiply here. Maybe let's do the next one, Ahmed. Maybe that'll be a little bit more clear. So I multiply by 0 because that is the element, that is this element right here. Right? So this is why we want to multiply by as many zeros as possible. Normally you would just skip this. You'd say, I know it's going to be 0, but here, let's try the next one and I'll show you. So we're going along row 2, right? So our next element is this one. So I'm going to add 5 times -1. What's the power? Two plus 2, perfect, because this is the 2 element, right? It's row 2, column 2. And then I'm going to cross out this row, cross out this column, and do the determinant of 3, 1, 2, 3. Okay, so Ahmed, does that clarify why I was multiplying by 0 in that first case and then by 5 in this case? And then because I'm going along row 2, the next time it'll be 0 as well, right? Okay, everyone else is good too. Does that make Karina, did I answer the like -1 answer? I mean, like, it's probably unsatisfying. The answer is just this is just the formula, right? But for me to give like a nicer answer, I kind of have to really go into the mathematics of it. Okay, and then our final element is here. So again, you don't have to do this. Okay, you don't have to put the -1 in here. But you don't have to put the 0 in here. You know it's 0. And we do it like this, okay? And so now at this point, well, let's ignore the zeros, right? The yellow stuff is all 0. The green stuff is all 0. So the only stuff that survives is the blue stuff. So I get 5 times the determinant of this 2 by 2. And we just remember that when you do the 2 by 2, you multiply the diagonals and you subtract the off diagonals. So this gives me 5 times 9 minus 2, and that's equal to 35, like that. Okay, and let's just double check. Everyone's okay with this? Is anyone not certain where that came from? Everyone's okay? Okay. I got you. Yeah, let's talk about it. So this right here, this 3 times 3 times 1 minus 2, this is this thing, okay? And you just have to always remember, okay, you have to know this formula. The determinant of the 2 by 2 is the diagonal AD minus BC. Okay, yeah, so that has to be there, right? In it's kind of hard to describe. I mean, that it has to be there, but it's hard to explain why it has to be there without getting into some really, really heavy mathematics, like why the pluses or minuses are there. And Julia, is that okay? Did that clarify that a bit more, or do you need more? Okay, yeah, you're good. Okay, so Christian, yeah, we ignore them because they're 0, exactly. In the tutorial, the TA gave a different way. What did they use? Aziz, do you know what Jeremiah's talking about? What the different way was?
I'm checking as we speak the tutorial worksheet, and I'm not sure what Jeremiah is referring to.
And so it would have mattered if like the yellow and the green weren't 0.
Oh, I think they're talking about like instead of, so you know how you did -1 to the power of the number? I think what was told to them in the previous tutorial was that you could just think of it as plus minus all the way across,
right?
And then
Okay,
you could just add the plus or minus accordingly.
Sure. Yeah, I mean, I guess you can do that. You just kind of have to be a little bit careful. I know that a couple of people are still bugged by the -1. So why don't let's do this over another row or column, just so that we can see that it actually does work, right? Kind of like no matter what row or column we use. So let's do it again, because I think, you can never practice too much. So let me copy this. And then I'm going to paste it down here, and then we're going to do it again, but we'll choose a different row or column. Okay. So do we want to do the really hard one? Okay, so I got a request for row 1, but I was kind of going to do column 2 because that was the worst one.
Oh, I was thinking column 1 just because there's a 0 as well there.
Yeah, I mean, like some people might want. Does anyone feel strongly about which one they want? Or, I mean, actually, row 1 is bad too, right? Row 1 is also bad, right? Let me use column 2. I think column 2 is the worst because, yeah, row 1 still is in some sense nice because it's going to start with plus and then go minus and then plus, but column 2 is going to start minus and go along that way. So let's go along column 2. Okay, so I'm going to get that the determinant of M. So once again, we're going to start here. So we're going to get this is equal to 5 times -1. Now we're in row 1, column 2, right? So row 1, column 2. I'm going to cross out these things to get the submatrix like this, right? Is everyone okay with that? Yeah, you could be an aga. It's definitely possible. Okay. Oh, so the submatrix. So you notice how I crossed everything out? So the submatrix is all the uncrossed out numbers, Jack. So you see that it's like 0, 0, 2, 3. Like look at the things that aren't crossed out, right? You get like 0, 0, 2, 3 here. Yeah, that's where those come from. That's why I've been crossing them out, is so we could see what that submatrix was. Okay, let's do the next one. So the next one is this one. So we're going to do +5 times -1, 2 + 2, right? We cross these out. So I'm going to the determinant 3, 1, 2, 3, like that. Okay, and so I am doing this one a little bit quicker. +2 times -1. So this is row 3, column 2. And then I cross these out. 3, 1, 0, 0. Okay. And now, again, we're going to use this fact, right? So the determinant of A, B, C, D is AD minus BC. So when I write this out, the yellow part is going to become 5 times -1, right? Because -1 to the power of 3 is -1, times 0 times 3 minus 0 times 2. Right, so that is going to be 0 again, plus 5 times +1 times 3 minus 1 times 2. And then the green part is +2 times -1, 3 times 0 minus 0 times 1, like that. So that again gives me 0. And if you evaluate all that, you just get, so only the middle part is non-zero. So you're going to get 5 times, well, look at that, 9 minus 2, 35, right? Same answer. Right? So it really doesn't work. And if you want to, try it along even a different row or a column. If you want to, like, try doing it over row 1. If you want, that's kind of another bad one. Can we calculate the -1 cubed? I'm not certain what you're asking.
I know the trick that people usually do is they start with like row 1, column 1 being positive,
Mm-hmm.
and then they just go from right to left, and they just alternate the signs as they go along.
Yeah, and you can definitely do that as long as you make sure you get the first sign correct, right?
It's exactly that.
Yeah, and so for those of you asking why it's +1, notice that -1 to the 2 + 2 is the same thing as -1 to the power of 4, and -1 to the power of 4 is just 1, right? Like -1 to an even power is equal to just 1. Oh, and is that what you're asking? Like why? Yeah, so, right? So here we had -1 cubed, but that's just like every even multiple of this is just equal to 1, right? So that's -1. Here we had -1 to the 4, which is 1. And here's -1 to the 5, which is equal to -1. So it just keeps alternating signs. And Naga, what you have to be careful of is it does alternate signs, but it doesn't always start with a +1 or a -1. You need to make sure that you get that first sign correct. If you get that first sign correct, then you can just alternate them if you want, right? Yeah, so as long as you do that, that's totally okay. And I see. Yeah, 100% you could use to the power of 4 if you want. Like if you guys don't want to write this as just -1 +1 and -1, you could actually like just write the powers as -1 to the 4 and -1 to the 5. That's totally fine. Okay, so is everyone okay? And like once you understand this algorithm, you could, in theory, do a matrix of any size, right? Because whether it's 4 by 4, and this is why I'm saying like don't use those rules, because that rule that was mentioned, Saris's rule or whatever, only works for 3 by 3. This procedure works for a 10 by 10, right? You choose a row or a column and just keep doing this process where you write down, the determinant of the 9 by 9, and then when you compute the determinant of the 9 by 9, you would do the determinant of the 8 by 8s inside of it, and so on and so forth, right? Okay, hold on. So in the blue, how do we know that 3 times 3 is before the? Because yeah, so up here it's always the diagonal first, and then you subtract the off diagonal jack, right? Does that make sense? Yeah, and Aruba says this as well, right? Yeah, top left first. And Angeli, that was just me working out this thing, right? This is 9 and this is 2. Yeah. Okay, does that make sense? Everyone's good on that? We're feeling confident in our determinants? It's not that they're chaotic, it's that they're tricky. And it's not even that they're tricky, right? It's like, here, let's go to the next one. I'll get the poll going and then we can talk about it. Determinants are actually a really high-powered thing. They're really quite complicated. So much so that even if you take, again, like 223 or 224, which are our dedicated linear algebra courses, right? These are courses where you will, for the entire semester, learn about linear algebra. And the way we teach determinants in that class is exactly the way that I'm teaching determinants to you, right? It's not like they get some secret access to some forbidden determinant knowledge. The reality is that determinants are super powerful and super strong, but where they actually come from and proving a lot of the properties that determinants have is quite complicated because they involve a lot of very high level, very complicated mathematics, okay? Yeah, Aiden, exactly. Yeah, that is a very good observation. Yeah, it's much better. And Curdy, don't be intimidated by the size of this matrix. Like once you start computing, you'll be like, oh, hey, something really cool happens. The truth, yeah, so the truth about why the signs alternate and why determinants seem so hard is because what you're actually doing is computing a volume, all right? Somewhere in the background, there is this, like in this case, in this 5-dimensional shape, there is this 5-dimensional matrix. In the background, there's a 5-dimensional shape that this matrix represents. And what the determinant is doing is calculating the volume of that shape, right? Now, obviously, it's very hard to visualize because most of you probably aren't very good at thinking in 5 dimensions, right? But there is a 5-dimensional solid that is occurring. And what the determinant is actually doing is computing the volume of that 5-dimensional solid. So, and it's actually even more complicated than that. I'm sweeping a lot of that under the rug, but that's why it seems so hard, because computing volume is actually very complicated, let alone computing volumes in like weird dimensions, like R7, right? So there's a lot of stuff going on there. It ends up being quite complicated. Okay, now, again, if you're plugging this octave, I hope you actually try and do this one by hand, because again, this one's really cool, right? Like I normally wouldn't give you a 5x5 if I didn't think that it couldn't really be done. And yeah, something really cool happens if you do this one by hand. So I really think that it is worth doing, and hopefully you see the cool thing yourself. Yeah, Brandon, absolutely. Like I wrote out the zeros in the previous step just to like, so that people could see the algorithm in its totality. In this case, obviously there are a lot of zeros. Just as soon as there's 0, don't even write them down. You can just kind of be like, I know what the answer is, so I'm just going to write down what the answer is. And you can skip the 0 stuff. Absolutely. Again, what I do necessarily in class isn't necessarily what you should do in your solutions, right? Because my goal here is to show you all or didactic reasons, right? Pedagogical reasons. I want you all to understand the process. But when you write solutions, you're writing them as if you were explaining to a classmate who understood the same as you. And so you can skip the trivial stuff, right? You can skip things that are obviously 0 and stuff like that, right? I include it just so that people can see what's going on. Because I promise you, in that last question, if I had skipped the zeros, people would have said, well, how did you, like, where did this stuff magically come from, right? And it actually would have added more confusion. So, I include those steps just to make sure everyone's on the same page.
I have a feeling a lot of people are putting this on octave and just getting an answer, but I might be wrong. I'm hoping I'm wrong, but
I'm sure they would tell us if they were. Who did this by octave? Who just plugged this into octave?
I want to see who the brave souls are. There has to be at least one.
Okay. Thank you for your honesty, Saris. I appreciate it. Right? Like, okay, Aruba. Yeah, we can do it. Ahmed, nice. I like it. Because why wouldn't you, Brandon? Right? Like, I mean, it's not worth marks. It's not an academic offense. I didn't say you couldn't use octave. It's just like, I think that there's a valuable lesson to be learned here. And again, even for those of you who use octave, please try and do this by hand, because I think that if you don't do this one by hand, you're really depriving yourself of an opportunity to see something that's happening, right? Like you do it by hand and you see what's happening and you're like, oh, there's a cool trick here that I can now generalize so that if I see this on a test or something, I just know what to do, right? And that you might not have that opportunity to do if you just plugged it into a computer.
I was gonna say, like on a test, especially if the numbers there are arbitrary, if you don't know how to do it by hand, Octave will not be able to help you when there's a lot of like letters in there instead of numbers. So learning how to do it by hand is also, I'd say, very important too.
And also, don't underestimate my ability to screw up a computer, right? To like get a computer to tell you a wrong answer. Because I used to be able to do it all the time. I could get like Wolfram Alpha and Simolab to give you the wrong answer. Because I could just make things complicated enough because I know how the computer's algorithm works that I could make it break and give you something total nonsense. Aruba, yes, it depends on what you mean, but I think you're kind of seeing it. Yeah. Okay, so we're at 60%. I'm going to close it in about 30 seconds here. So let's get those in. Let's see where we are.
I would recommend in this question using row number 2 to do it.
Yeah. And then, yeah, if you want to use Octave after to check your answers, go crazy. Yeah. I mean, I don't even expand over a row or a column. I can just see what the answer is.
Yeah, I agree for this case.
Right. Okay. And this is actually related. Hopefully, remember I was talking about that there was actually the secret way of computing determinants faster, and this is related to it. Okay. Yeah, dude, that's exactly the secret answer here is that, so you're all, again, the class was correct. You said -12. And what you notice is that -12 is just the product of the numbers on the diagonal, right? And that's it. If I give you one of these matrices that is, so this is called an upper triangular matrix because it has all zeros beneath the main diagonal. And if you have such a matrix, the determinant is always just the product of the diagonal elements. And same thing, if you have an upper triangular matrix, so all the numbers above the main diagonal are 0, then again, the determinant is just the product of the diagonal elements. Okay, so in this case, what you'll hopefully notice is that 1 times 2 times -1 times 3 times 2 is -12. So that is the determinant. Now, if you're doing this by hand, right, that's what I wanted you to see, is that if you actually do this one by hand, you can see why this is true. So let me write this matrix out again. So this is question 3. And I'm not going to include the zeros for this one just because that would take a really long time. So I'm going to skip the entries that are obviously 0. Okay, so you'll have to forgive me that. So we've got this matrix. I'm going to give it a name. Let's just call it M again. Okay, so we've got 1, 3, 7. And we know that most of these numbers don't matter. Maybe let me put my brackets in after 0, 2, 3, 1, 5. 0, 0, -1, 3, 12, 3, 6, 0, 0, 0, 0, 2, like that. Okay, now naturally, right, let's expand along the first column, right? We can use a diagonal when all the numbers below it are 0. Yes, yeah. Or Jeremiah when all the numbers above it are 0. Yeah. Okay, so we're going to expand along the first column. If I do this, I get 1 times -1 to the 1 plus 1 times, right? And then I cancel all this stuff out, the determinant of the submatrix. 2, 3, 1, 5, 0, negative 1, 3, 12, 0, 0, 3, 6, 0, 0, 0, 2, right? And actually, you know what? I'm going to keep track of the numbers, okay? So the numbers that we multiply by, I'm just going to keep track of them. And everything else is 0, right? Yeah, you could use the fifth row as well. That's perfectly fine. It basically, it's going to give you the same answer, right? And the fifth row uses a bunch of zeros as well, so that's totally okay. I just like the first column because I like to start in the top left whenever possible, but Ahmed, yeah, you totally get the same answer, right? And so even better now, you did it one way, you're going to see it a different way. Maybe it'll even add to your understanding. So, okay, so same sort of thing here. I'm going to use the first column. Ahmed, you'd probably want to keep using the bottom rows, depending on how you did it, right? So I'm going to use this number and expand along this. Actually, let me draw this in blue so we can keep track of which number we're doing. So this is going to be equal to 1 times, I'm going to get rid of this because we know that's just plus 1, times the determinant. Maybe I'll write this in a big old bracket here. So 2 times, I'm using blue, sorry. This is what happens when you try and use different colors. 2 times negative 1 to the 1 plus 1 times the determinant of that submatrix. 6, 0, 0, 2, right? Again, I'm gonna, this number here is just 1. And I'm gonna keep, I'm not gonna multiply this 2 in, I'm gonna kind of like leave it so that we can see it show up. And then for my next step, I'm gonna expand along, again, the 1, 1 element. So this is going to be equal to 1 times 2 times negative 1, because that's the element here, times negative 1 to the 1 plus 1. That's always going to be 1, right? Hopefully you're kind of seeing that pattern. 3, 6, 0, 2. Again, this is just 1. And then the determinant of this thing, this 2 by 2 matrix, is just 3 times 2, right? So in total, what do we get? So we got 1 times 2 times negative 1, and then times these two numbers, which I'll write in red, times 3 times 2, right? And so if we look at these numbers, and I zoom out so that we have the original matrix in front of us, we notice that those are exactly these numbers along the diagonal, right? And you can imagine that, like, it wasn't, there was nothing about those numbers on the diagonal that were special. It's just that those, every time I expanded along the first column, those were the numbers that survived along the way, right? And that, yeah, this sort of pattern is going to hold generally. It doesn't matter how big the matrix is. If you do the same sort of procedure, there are so many zeros constantly that you're always just going to pick up these elements in the diagonal, right? So as kind of like a nice lesson there, we can say, you know, given an upper or lower triangular matrix, upper or lower triangular matrix, the determinant is the product of the diagonal. Okay, so you just multiply all the numbers on the diagonal together. So triangular means, again, there is a formal way of defining it, but I think it would be confusing. It means that all the numbers above the diagonal are 0, or all the numbers below the diagonal are 0, right? So if we look at this matrix, what we notice is that there's this like triangle here of of 0 numbers, right? Right, so that's what we mean by triangular, right? Is that there's that triangle and it's just directly beneath the diagonal. Yeah, and I would say that's okay. Yeah, you can use that. Okay, Christian, let me take a look at this. Actually, let me kind of get the next question started and then I'll take a look at that. But Yeah, exactly. And Ahmed, so this is, Ahmed, I think there's kind of a good point here, which is from your comment, which is, this looks, where is that comment? So it looks pretty simple, but it also kind of looked intimidating. And that kind of happens a lot, right? Like if you, it's very common that you'll be given a problem and you might panic at first because it looks intimidating. But instead of panicking, if you just kind of proceed with what you know, you might find that the problem is simpler than you thought, right? And I think I've said this before, the last thing that you want to do is get all clammed up because you panicked. So don't panic, just apply the techniques that you know, and you might get lucky and it turns out that the problem is easier than you thought it was, right? And yeah, exactly. If there are numbers in the part where they're all zeros, then you're in trouble, right? No, it doesn't. So it doesn't work if you're not triangular, right? So if you're not triangular, then you can't multiply the numbers on the diagonal. That doesn't work. But this does actually lead to a strategy which does work. So first of all, I'm going to skip this one. I want to do this question. No, actually, we're going to do this one first. Let's do this one first. Oops. Okay, so let's do this one. So there is a strategy to computing determinants faster than doing the long way. And the way to do it is to start row reducing, right? So when you row reduce a matrix, remember when you, like in the process of row reducing, you actually turn a matrix into a triangular matrix, right? Like you try and make ones beneath or zeros beneath all of your leading ones, right? So that's something that you're trying to do. And then once you get it down to a diagonal matrix, you know what the diagonal matrix is, and you can just multiply all of the numbers on the diagonal and get the determinant. But here's the problem. When you apply the row operations, you change the determinant, right? So the row operations actually change the determinant. However, they change them in a very precise way. The row operations, like for example, if you swap two rows, your determinant picks up a -1. If you add a multiple of one row to another, the determinant doesn't change. And if you scale a row by a multiple of, say, 7, then you multiply the determinant by 7 as well. And so what this means is that if you keep track of all the row operations you used to turn your matrix into a triangular matrix, you then compute the diagonal, or you compute the determinant, and then you undo the changes that the row operations made to get back to your original answer. Does that make sense? Like that's basically the trick, right? So if there are a couple, if your matrix is very near triangular, you row reduce it so that it is triangular, and then keep track of the row operations that you used and undo them so that you can get the original determinant. I mean, like we're never going to use this, Ahmed, so I wouldn't worry it too much. But yeah, it's basically just that when you row reduce, you can row reduce a matrix to a triangular matrix, compute the determinant easily, but you have to figure out what you did, like what changes did you make to the determinant by row reducing, so that you can undo those changes later. And Ariana, yes, exactly. It is incredibly similar to assignment 4. Okay, so I'm going to give you about 30 seconds because I do want to hit this point home, and the class is overwhelmingly incorrect. So I'm going to give you 30 more seconds to get your answers in. So this is 100%, if we were an in-person test, I would give you this as a multiple choice question, just to wreck people.
I can see that. Have you done it before? I feel like this looks familiar for some reason.
I don't know if I've given this exact one. Yeah.
Something similar though, I feel like.
So Connie, that matrix you have and this one are actually the same. They have the same determinant, right? Yeah. Okay. So we're going to end the poll. We're going to share the results. So overwhelmingly, the class said C, and the answer is absolutely not 1. Okay. The answer is not C. Now let's take a second, everyone. Read what the question says. Read what the question says. What does the question say? I'm not asking you for the determinant of this matrix. right? You all agree? I'm not asking you for the determinant of the identity matrix. That is 1, right? That would absolutely be correct if that's what I asked you, but that's not what I asked you. I said this matrix can be row reduced to the identity matrix. What is the original determinant, right? Right, you don't know what the actual matrix A is. And so in this case, the answer is it's impossible, right? Yeah, and here's an easy example. So the bonus question said, give to an example of 2 matrices that both row reduce to the identity and have different determinants. Here, let's do like 1, 3, 1. Okay. Neither of these matrices are in RREF. You agree? Yeah, exactly. It says it can be row reduced to, right? We got to read the question. This is what I'm saying. And on a test, I imagine you'd read the question more carefully, right? I think people kind of maybe jump the gun and we're like, oh yeah, I get the idea here. But the question said can be row reduced. So I think you all agree these matrices are not in RREF, right? But it's very simple to row reduce them to RREF, right? You would just scale the first row in the first matrix case and the second matrix, or the second row in the second case. What's the determinant of this matrix? 2, perfect. What's the determinant in this case? 3. So here are 2 matrices that both row reduce to the identity, but have different determinants, right? Yeah. Okay, but now, and I know we're running out of time, so I want to do this one really, really quick. Oops, my hand touched it and damn it. Did I open Steam by accident?
You did. It's updating.
Of course it is. Where is? Of course I'm running out of time, and now is the time where I need to like not be running out of time. I know. I'm sorry. I just so easily distracted by games. I just needed to play. I've really fallen out of game recently. I've had a lot of trouble finding any enjoyment in gaming.
I'm on that level too. I had a lot of games I played religiously, and now there isn't really much.
I'm having a lot of trouble finding pleasure. I do one game I absolutely love though and can't recommend enough. Maybe it's just because I'm an old man now, but like Dyson Sphere Program is phenomenal. Like I've just dumped such a stupid amount of time into Dyson Sphere Program. Yeah, no, I will never try League.
Me neither. Me neither. I have a very strict no-go for that.
Mm-hmm. Yeah. Yeah, Gerpertap, exactly. I feel the same way.
It's funny because now that you said that for the previous question, now people are answering this way, but that's not
right. Yeah, I think we're going to be wrong again.
Yeah, it looks like it. I think they're taking the logic they took from the previous one and they're rolling it over, but the logic does not roll over in this case specifically.
All right, 30 seconds, people, because the lecture is about to end, and I want to make sure that I can kind of answer this quickly before people run away.
I have my tutorial in a minute as well, so I'm gonna hop off in a minute. But I see now that I said that like all the other options are shooting up in popularity.
That's right. People are just guessing. Okay, so people started answering D because that was the same answer we had from before, but actually no. In this case, the answer is B. The answer is 0.
Mm-hmm.
And why do we know? Can anyone tell me? Why do we know in this case the answer is 0? No, not because the determinant of this matrix is 0. So that actually is a common mistake to make, but why? So if you row reduce a matrix to get to this, is it invertible? Yes or no? If this is the RREF, right, this is not an invertible matrix, right? What is the determinant of a matrix which is not invertible? It's 0. That's why the answer here is 0.
Mm-hmm.
Does that make sense? And Ahmed, exactly. That's how we know it's not invertible, right? Is because there is no leading one in that third row. So the matrix is not invertible because this is its RREF, and a non-invertible matrix has a determinant of 0, right? Yeah, so Ahmed, you kind of like got the right answer, but for the wrong reason. But Yeah, it's the same. It's the same sort of idea, right? This has determinant 0 because it's not invertible, and a matrix which rho reduces to this is also not invertible. So it's close, but like that's not the moral reason why the answer is 0, right?
I'm gonna go start the tutorial here.
Okay.
So
see you later, Aziz.
See ya.
Weights, the matrix has to be invertible first to determine the determinant. No, so you don't, a matrix doesn't need to be invertible to have a determinant, but the determinant tells you whether the matrix is invertible. Okay, so this is an important fact. It like I want to make this point because it's very important, especially for eigenvalues and eigenvectors. And it's easy to miss, I think, in the book and the notes. And I think I did talk about it in the videos, but I think it's a relatively quick thing and it's easy to miss. A matrix is invertible if and only if its determinant is not 0. Okay, so if your determinant is not 0, you are invertible. If your determinant is 0, you're not invertible. And the opposite is true as well. If you're invertible, you have a non-zero determinant. If you are not invertible, your determinant is 0. Okay, so having a 0 determinant is equivalent to not being invertible. And that is super important when we talk about eigenvalues and eigenvectors. And so for those of you who have watched those videos, one of the things we talk about is that characteristic polynomial, right? Which is the determinant of that special matrix. And the reason why we're looking for the roots of that polynomial is because we're trying to make that determinant 0. We're trying to make this matrix non-invertible, right? That's the entire reason why the characteristic polynomial comes about. We're trying to make that matrix non-invertible. So we want the determinant to be 0, which is why we're finding the roots of that polynomial. Okay. But you see, Jeremiah, like that's phenomenal because that's what I want, right? That's literally learning, right? That's what learning is happening. Because what you do is you feel like you get a concept. And then what I do is, and this is, I hope that this is a sign that I'm doing things right as well. So what I do is I try and build you up and give you an intuition for a concept, but I know your intuition isn't perfect. So what I'm going to do then is I'm going to slap you and be like, hey, by the way, no, your intuition isn't perfect. Here's a little way in which your intuition is incorrect. And then I explain it to you. And by doing this, I'm trying to shape your intuition and your understanding in such a way that you really understand the material, right? Because it's so easy to think that you understand the material, but you just haven't seen the right examples yet. And so I want to break you down and then build you up, and then kind of break you down a little bit and then build you up a little bit stronger, break you down a little bit more and build you up stronger, right? It's like I'm forging you in a fire, right? Like you're like a sword, right? I pull you out of the fire, I smack you a bit, I put you back in the fire, I pull you out of the fire, I smack you a bit. Exactly, it's a math gym. Right? That's what it is, right? You got to hurt, you're constantly tearing those muscles in order to make your muscles bigger. And that's exactly what we're trying to do here. And you talk to any of those guys, they feel strong, but every now and then they got to lift weight that, is too heavy for them, right? Because you got to know what that feels like. So that's exactly what we're trying to do here. And I think people don't appreciate how much things like, learning an instrument, playing a sport, or weightlifting. And we use weightlifting as an analogy for learning a lot. There are a lot of analogies between what we do in class and those sorts of things, sports, musical instruments, weightlifting, right? And again, that's part of why we do this flipped style, right? If I was your personal trainer, you're not going to get stronger by watching me lift weights, right? That doesn't do you any good. So I can show you how to lift weights in like a video, and then you come to class and you lift some weights, right? And I help you with your form and stuff. And that's what we're doing in this style of a lecture, right? You watch me lift weights on your own time to try and get the form. You come to class, you lift weights yourself. I help correct your form, and eventually you get stronger as a result of that. That's exactly what we're doing, right? So that's the idea, okay? All right, so obviously for those of you who have to run, we're going into office hours right now. Again, give me a couple minutes, just refill the water and stuff like that, and then I'll come back and answer any questions. Go through your stuff, figure out what sorts of questions you want me to answer for you, and I'll answer them all when I get back, but give me a couple minutes and I'll be right back here. Okay, see you in a bit. Okay, so a similar question to 1B on the assignment. Sure. So, I mean, there's kind of been a typical thing that we've gone through with a couple of students. Let me, I'm willing to bet there are lots of people who would probably be interested in this. I imagine there's no concern if we do things this way. Okay, so some of you might have already received this hint from me, and if you have, I'm sorry, you're going to see it again. But what I think that we should do, the first thing let's try is let's do this. So somebody compute for me. I'm not going to do it. I want you to do it. No, yeah, let's change a different number. Let's use 7. Okay, well, what is this? If we do that matrix multiplication, these of course are 2 by 2 matrices, not 3 by 3. But if we do this, what do we get? Okay, so A plus 7C, and no, it's matrix product. Yeah, so we want a matrix product. So we get A plus 7C. Okay, what else? So second row, yeah, okay, so we're gonna get a C here. So first column is done. Now let's work on the second column. What do we get? D in here, okay, sure. Yeah, and so what's the top right? B plus 7D, right? Yeah. Okay, and again, let's just make sure we understand why that one is. So we would like do the dot product, and Ain, maybe that's what you meant by the dot product, but we would do these two, right? So right, I've got a column and a vector, and then I dot product those together like that. Yeah, exactly. Yeah. Okay, does everyone agree that this is the matrix that we get? Okay, what row operation was this? Row 1 plus 7 R2, right? So this was row 1 plus 7 R2 into row 1, i.e. in the 2 by 2 case, this is T127. Do you all agree? Like in the 2 by 2 case, assuming that the notation was the same, this is T127, right? It says take row 1 and add 7 row 2 to it. Okay. Now, is there anything special about the number 7? What would T, if I just change this number, I wanted this to be, well, let's not use C here because I've used C in the matrix. If I wanted this to be K, what would I change this matrix to do? Like what number here would change? Yeah, the 7 would change, right? Okay, so like that. Okay, can you guess what T217 would be? So remember, this means that I want to do row 2 plus 7 row 1 into row 2. If you just had to guess, like totally out of the wild, what do you think the matrix would be? So if I now switched and did row 2 plus 7, yeah, Brandon, exactly, perfect. And you can check that, right? So if you actually check that, you can check that 1071. A, B, C, D. So if we actually do this, what do we get? So we get A, and then we get 7A plus C, and then we get B, and then we get 7B plus D, right? And that is exactly row 2 plus 7 row 1, right? Okay, so your goal now is to generalize this to 3 dimensions. And obviously it is a little bit trickier because there are more places where something could happen. But the idea is that just try one, right? Just try something and see what happens, right? Brandon, yes. Yeah, that does end up being the answer. Yeah. Okay, so the idea is you want to generalize this idea, and same thing, right? If I put a K here, we want to generalize this idea to 3 dimensions. So what I would do if I were you, just guess what you think the answer should be and check it for 1 matrix, right? Like just try and guess what T13K would be. See if you can write it down. Nobody put it in the chat because technically that would be giving away an answer. But But guess what you think that number should be? Multiply it into a big 3x3 matrix, A, B, C, D, E, F, G, H, I. See if it worked, and then argue that, yeah, that's what, see if you can figure out what the pattern is, and then argue and explain to us what Tij, K is for general I and J. So does that make sense? Does that hint help? Okay, sweet. Is everyone else okay? Like, did that make things a little bit easier? Okay, because I'm gonna move on, and unless I start to hear some protest. Okay. So yeah, okay. So what I did here is I literally just blindly, I said, listen, let's do this thing. So I'm going to multiply this matrix on this thing, and I got this, right? And what we recognized is that in doing that, this matrix had the same effect as doing this row operation. Okay. Sure, I can explain the T12. So T12K, the definition of this is that it is precisely the matrix which does this row operation. Right? So if I do T12K acting on a matrix A, then that is the same thing as having done this row operation to A. Okay, that's what the definition of T12K is. Okay, it says that is the definition. It does that row operation. So for this matrix, we actually just did the multiplication, and we get this thing. And we see that that is precisely this row operation, right? So that means that this is T12K, because this matrix performs that row operation, right? So this, whatever your row operation is, so the question is, I use numbers instead of A, B, C, and D, like in here. I mean, your answer has to hold no matter what numbers you put there. And the problem is that if you choose numbers to put there, you could have gotten the right answer by accident, right? Like your matrix might work, but it might work only because they worked for the particular numbers you chose. So you want to be able to argue that your answer works no matter what, right? And that's the critical thing to be able to do. Yeah, absolutely. You can use letters for this if you want. What you might want to do instead of A, B, C, and D is like A11, A12, A21, A22. If you want to use that as your matrix instead, you can. It's a little bit nicer because you don't like run out of letters. So you absolutely can do that. But the idea is, right, you are looking for a matrix such that when you multiply it on the left, that gives you the same effect as having applied that row operation. Right? Is everyone okay with that? Because I know that there was some confusion there. I just want to make sure everyone's okay, because I don't want you to get a question wrong because you just didn't understand what the question was asking. Do you have to prove that your answer works? I would say no, but you might want to give an example. I think like just saying, hey, look, here's a particular example of it, and if I apply it to this like general matrix A, we notice that it does what I want it to do, and therefore all the other ones do as well, right? Just kind of give an example showing. I think that would be the best way of doing it. It's not the only way to do it, but I think that would be the best way to do it. Here's how I would write it. I'd write like the matrices are of this form. And as an example, here's a particular one. Notice that when I multiply it by this general matrix A, it does exactly what I said it would, right? Yeah, exactly. Example and general description, I think, is probably the best way to do this. I've never asked you to prove anything in this course, and I never will, because proofs are a whole different beast. Like when you ask people to prove stuff, that is a complicated thing to do. So I would never ask you to do that. I just kind of want you to give me an idea of how it works. When you multiply it, it has to equal to a matrix though. So it does, right? Okay, let me put it like this. So let's okay, I'm going to use an actual matrix for this, but you are not allowed to. But I'm just doing this to try and demonstrate the point, okay? So let's say that I gave you this matrix, 2, 8, and 4, 5, something like this, okay? So I'm going to row reduce this matrix just a little bit. So maybe I would do negative, so I would do row 2 minus 2R1 into row 2. And if I do that, I get 2, 8, 0, and then row 2 minus, so 5 minus 16 is what, negative 11. And then I am going to do 1/2 row 1 into row 1. So that would give me 1, 4, 0, negative 11. And then I would do, and let's just stop at REF. Okay, so negative 1/11 R2 into row 2, 1, 4, 0, 1. Okay, so I haven't done anything there with these SIJs, U's, T's, anything like that. This is just our standard row reduction, right? So I haven't done anything crazy like that. Now, what I'm saying is that this row operation is the same thing as T21 negative 2. This row operation is the same thing as U1 1/2. This row operation is the same thing as U2 negative 1/11. So to turn this matrix A into this matrix B, that is the same thing as doing negative 1/11. Like that, right? Yeah, T21 because I'm taking row 2 and adding negative 2 row 1 to it, right? It's not that I've written it backwards, it's that every time I do it, so remember when I am applying the operations, I apply them to the left. So what's the first operation that I do, right? I do this step first, so I apply it to the left of A, right? And then the next step that I do is this one, so I apply it to the left of that answer. And then the next step that I do, I apply to the left. So you just keep applying them to the left. So if you want to think about that as being backwards, you can, but it's basically like every time I do another operation, I just apply it to the left of what I've done so far, right? So what you're looking for is matrices which do this, right? They're gonna, in our case, they'd be 2x2 matrices which have this effect, therefore, you could have, instead of doing the row reduction, you could have just multiplied by these matrices in order to compute the row reduction. Does that make sense? Does that help? And what we just found, and I'm kind of like fine telling you what these matrices are because this is the 2x2 case. Okay, so this here, so we've got T21 of negative 2. We already said what that is, right? It's going to be 1, negative 2, 1, 0. Does anyone know what this one is? What U1 of 1/2 should be? Yeah, exactly. Yeah, when you apply it, you add the most recent one, you kind of throw it into the left side. While people are thinking about that, let me answer this question. I said SIG is this. Yeah, that's a great description. Yeah, Brandon, I think that's a great description. Yeah. Like, okay, and for everyone, right, when I say it's enough to describe your matrices, what your test for that should be is if I gave this to another student in the class, could they write down what the matrix is, right? So your description needs to be complete enough. Like it doesn't necessarily need to be mathematical. You can describe what the matrix is, but you should be able to give it to a friend in the class and they should be able to write down the matrix based off of your description, right? So does anyone know what U1 1/2 would be in this case? Just out of curiosity. And you can tell me because this is the 2x2 case, so this doesn't matter. Brandon, yeah, exactly. Right, and you guys can check if you multiply any matrix by this thing, 1/2, 0, 0, 1, you get back the same matrix except that the first row has been multiplied by 1/2, right? And This thing, you can imagine, looks the same sort of way. -1/11, 0, 0, 1. And so what you would get is 1401 is equal to -1/11, 0, 0, 1 times 1/2, 0, 0, 1 times 1. What did we say that matrix was? 1, 0, -2, 1 times the original matrix, 2, 8, 4, 5. Right? And so these matrices are playing the role of the row reduction, right? They are the row reduction steps. So Agam, the T21 we had found before, right? So T21 we had talked about right here. So, and we actually did it, right? So I said that this is T21K. And when we did the computation, we saw that it did in fact take row 2 and add K times row 1 to it, right? So that's how we knew that. And then Brandon was kind enough to give us this answer. And you can check it, right? Check that if you multiply by this matrix, 1/2, 0, 0, 1 times A, B, C, D, you get 1/2 A, 1/2 B, C, D, right? So that's the same thing as just scaling row 1 by 1/2. And Jack, is your holy a good holy? Like, is that because like, yeah, it makes sense now, or? Yeah, I hope so. I hope it's the realization holy. I mean, that's great. Yeah, like, I mean, that's phenomenal to hear that. Okay, that's okay. Yeah, there's nothing wrong with that, right? You got lots of time. But yeah, I mean, the part of the goal of this exercise is to really get you playing around with matrix multiplication and really thinking about how it works. And the best way to do this is not to just have you multiply matrices, but to have you like think deeply about what matrix multiplication is doing and what you want it to be able to do, right? But yeah, assuming that I've done everything correctly, you can go and you can plug this into Octave and you should get this matrix out. And that is the same thing as having to row reduce that matrix, right? Okay, so is everyone okay? I know. Yeah, and absolutely. And you know what? So I get a direct message. It's like saying, you know, we have to work backwards to what we learn. And yeah, absolutely. And, you know, pedagogically or understanding things, I mean, I don't expect any of you to know this, but like there are multiple stages of understanding, right? Typically there's about 5, and there are things like procedural and so on and so forth. And one of the things that we try and develop is specifically, you know, attacking things from multiple directions, having multiple tools, multiple perspectives, being able to explain things in different ways, because doing all of these sorts of things is what solidifies your understanding of a concept, right? Okay, so for T21, we basically guessed, like I basically gave you the answers and I said, you know, check that this works, right? So for T21, I said, this is T, actually Brandon technically gave us this one, so that this was the answer. And then, excuse me, then we wanted to check that it was the correct answer. So we multiplied it into A, B, C, D. And if it is the correct answer, then we should get the same thing as if we did R2 plus KR1 into R2, i.e. we should get A, B, C plus KA, D plus KB. And then we actually do the matrix multiplication and we compare these two matrices. And yeah, those are the same, right? Like I wrote the second row a little bit different, but those are the same. And so therefore, this is in fact the matrix which gives you that row operation, right? Multiplying this matrix is equivalent to applying that row operation. For U1 and U2, I would suggest that you just try it. Try multiplying a matrix by this thing, or maybe let's call it K again. A, B, C, D. Okay, actually do this matrix multiplication, see what you get, and then ask yourself what row operation is that, right? Can you solve it without defining I and j? So, oh, and it kind of depends on what you mean by that. I mean, in order to be able to write down a matrix explicitly, you have to say what I and j are, right? But it is possible to describe the matrix for a general I and j, if that's what you mean. Like you can just say the matrix Tij is this thing, and use I and j in your description. You can absolutely do that. Like you don't have to specify I and j. The last operation will be the extreme left, right? So every time you apply an operation, you apply it to the left of the total. So I took A, and then I did row 2 minus 2 row 1. So I applied that to the left, right? Then I scaled the row by half. So I multiplied that on the left, and then I scaled by 11. Or sorry, this should be U2. Right, because I scaled. How did no one say anything there? 1 negative 1 over 11. And so then I scaled row 2 by 1/11th. So I apply that to the left, right? So you're always just applying the operation to the left, because applying it to the left is actually what gives you the row operations. If you apply it to the right, you'd actually get column operations, but we don't want column operations, right? We're not allowed to do column operations. Okay, so Aiden, what I'd suggest is, there's kind of a pattern here. Oops, and the same general pattern holds even in 3 dimensions. But when you're trying to figure it out, just guess what you think the pattern might be, right? Like look at our examples here for T12 and T21, right down here in the bottom left. Look at those examples and say, oh, I wonder if this matrix in R3 does anything, right? And if you want, plug it into octave, right? Don't necessarily do it out by hand. Choose a value for K, choose a number like 7, and choose a random matrix and do the multiplication and see if it worked. And then use that to guide your intuition and see if you can use that to figure out what the matrices should be. There's a nice pattern, right? Like I promise you, they're all not like crazy or random or anything like that. There's a very nice pattern for all of these matrices that lend themselves to very nice and relatively straightforward descriptions. Okay, they're all fairly simple looking matrices. They're not like crazy or complicated. There's lots of zeros. You just got to figure out where to put the non-zero things, really, right? That's what it comes down to. Can I just translate the row operation to RREF, then use RREF? I'm not quite certain what that means, Jeremiah. You might have to like give me a little bit more there. So you're going to use the row operations to get to RREF. No problem, I can't. Right, so you translate the row operations to RF. Yeah, I'm not quite certain what you're saying, Jeremiah. So if you can elaborate on that a little bit more, I'll try and answer your question. It's a matrix which does a row operation, right? Like when we first defined row operations, we had no concept of matrix multiplication. But what we're saying now is it turns out that there is a matrix that you can multiply by, which does the same thing as that row operation. Right? Like if I take 3, 0, 0, 1 and multiply it by A, B, C, D, this gives me, 3A, 3B, C, and D. And that would be the same thing I got if I applied this, right? So what I'm saying is that this operation is the same as multiplying by this matrix. So this is U13. Okay, good. Does that make, I assume that was like a realization of, right? Yeah, I mean, I think the problem, so I think maybe part of the problem came is that we were in different, yeah, I mean, this is awesome. I'm getting a lot of wow, like understanding realizations, and that makes me happy. I think part of the problem is that we started with T, and T is the most complicated of the row operations, right? Octave can take variables, but it uses Maple's kernel to do it. Otherwise, you probably want to use Symbolab or Wolfram Alpha to do it, Owen, if you want to do it that way. So I think part of the problem is like, I would have started here, but the question was specifically when I was asked it at the beginning of office hours was to do it for TIJ, right? Because that's the most complicated one. And I think the problem might just be that we were as a class at different points in understanding what the assignment was asking. This is in some sense the easiest one, right? Or maybe the most illustrative because you can see what's happening, right? Like this is a relatively simple row operation. It's not add a multiple of one row to another, which is complicated. So yeah, hopefully that makes sense, right? I'm saying that matrix, multiplying by that matrix is the same thing as performing that row operation, right? Okay, hold on. I'm a little bit behind in my messages. For Q1 part 1 on the assignment, it says RI, RJ. So we're finding a matrix that will switch those two rows. Exactly. Yeah, exactly. Can we use some else other than something else other than, yes. Yeah, you can use whatever you want as long as you say what it is. So if you use Wolfram Alpha, just say by Wolfram Alpha, that's fine. And then Christian, so the 3R1 to R1 operation is the same as multiplying those two matrices. Yes. Yeah. Right. And it doesn't matter, right? Because the matrix A here, right? This matrix was general. Every matrix is of this form. You agree? And so multiplying by that matrix is the same thing universally as multiplying the first row by 3 and putting it in back in the first row spot, right? So that's universally true. So performing that row operation is the same thing as multiplying by this matrix on the left. Okay, so does this help? Like, and I mean, again, this is only the 2x2 case, but like the 3x3 case is very similar, right? Very, very similar. So would you apply the, no, so which both matrices? What are the two matrices you're talking about here? So here, this is, let me just kind of get this stuff out of the way. This is U13, U13. This is the matrix A. This is just A after that row operation. So we usually don't give it a name. No, U13 is the row operation. Right? Like look at the original matrix, okay? Like completely ignore U13 for now. Okay, this is 3R1 into R1, right? That is that row operation. Let's get rid of all this. You agree, right? That makes sense? Okay. So what I want to do is say, instead of doing that, I want you to tell me what matrix to put here that does the exact same thing. Such that when I multiply U13 into that matrix, I get that matrix on the right. Okay, and yeah, okay, good. And it turns out you can check that this matrix does it, right? That is the matrix that you multiply into A in order to get that row operation. No, and this is U1. So we want to be careful because there's 3 different row operations, and so we've called them different things, right? So we know we can flip 2 rows or interchange 2 rows. That was the S matrix. We can scale a matrix. That was the U. And then we can add a multiple of one row to another. That was the T matrix. So we don't want to confuse those notations there. even though technically what you wrote down kind of makes sense, we just want to be careful we're using the right notation, right? So Davin, what you'll notice is that when we scale a row, there's only one row involved, right? Yeah, it only deals with a single row, whereas the other two operations deal with two rows, right? So for example, the swap operation flips row, say row 1 and row 2, and that's why it has two numbers in it, because it needs to tell us which two rows we're operating on. But scaling only operates on a single row. So it only has that one number, I, which tells us which row to scale. So in order to obtain U and T, we need to do row reduction. I would say no, you're basically just guessing what they are. Like based off of what we've done today, for the 2x2 matrices, like I've kind of written them all down for you. You're just now trying to figure out what they should be in 3 dimensions instead. Yeah, so you're just kind of guessing. The T operation, okay, yeah, I mean, I don't mind doing it again. T214, yes, exactly. So let's do that one, Jeremiah. So we have A, B, C, D. So this is me explaining what I did earlier again, but in this new way that hopefully helps make sense. So Jeremiah, let's do your operation, which is row 2 plus 4 row 1 into row 2, right? And so if we do this, I'm going to get A, B, C plus 4A, D plus 4B, right? Everyone agrees, right? That's what happens if I take 4 row 1 and add it to row 2. And again, now what I want to do is replace that with T214, whatever this matrix is. Like this. And it turns out that the correct answer here is this one. Okay. And you can check that, right? You can actually do the multiplication and see that that works. So that is what that would be. And Jeremiah, that, like, I know that's not what you asked, but I wanted to use it to answer some other people's questions. But yes, your statement is exactly correct. That is what T214 would be. And that is the matrix which does this in the 2x2 case, right? Yes, yeah, the matrix you get is different, right? Like you notice that this matrix, which is U13, is fundamentally different than T, right? So there's 3 row operations, and there will be 3 different styles of matrices as well. So how about for, it confused me because 3 is only applied to row 1. Yeah, but it's only supposed to be applied to row 1, right? Like when we write right, we're only applying that to row 1, right? So did I misunderstand your question, direct messenger? There's no T. This is the U. U corresponds to this operation, not T. Yeah. Yes, that's what I was trying to say. Like, it's a different row operation, right? The U is the scaling operation. S is the swapping relation, and T is the add a multiple of one row to another operation. Right? So does that make sense? Right? So CRI into RI, that's UIC. Right? Flipping row I and row J, that's S. And then doing RI plus CRJ into RI is TIJC. Yeah. No. Yeah, don't use a single matrix to find all 3. These are 3 different matrices. So write them down separately. Don't put them together. Don't try and find one matrix which does it all. Yeah. Ariana, absolutely. Yeah, you can. And I'm sorry, I think somebody else was asking numeracy questions too, but I kind of got caught up in this. So if you ask me a numeracy question, please just ask it again so I can find it. But Ariana, absolutely, you can use factorial notation. Okay. So, or 3b maybe, because 2 doesn't have a part B. I really should start numbering the subparts A, B, and C and stuff like that too. Okay, so yeah, I mean, this is, so did anyone compute? No problem. Yeah, no problem. I'm glad it makes sense. So did you compute like f of 5? Did anyone compute f of 5 from numeracy? So I guess numeracy 3 part B. So what is f of 5? Like, let's say you don't know what the final answer is. Like, how would you compute it? So what is the equation? So f of 5 is equal to what? Here, maybe let me write it up too. So in case you didn't. All right, so this is what you're told. Yeah, okay, great. So it's 5 times f of 5 minus 1. So that's 4, right? Okay, so how do we compute what f of 4 is? So we just do it again, right? Yeah, sure. Okay, so but let's write it out. Yeah, okay, perfect. So f of 4 then is 4 times f of 3. Okay, what is f of 3? 3 times f of 2, perfect. F of 2 is, thank you. And f of 1 is 1 times f of 0, which is 1. So we can just, put the ones in here if we want. Exactly. Okay, and you can see that if I were to ask you like what f of 100 is, you don't want to do it. 100 is f of 100 is 100 times f of 99, which is 99 times f of 98, which is 98 times f of 97. Like, that's a lot of work, right? But hopefully you can see what the pattern is that every time you just you peel off the number, and then you get f of the next number down. So then you peel that number off and you get f of the next number down. So you peel that number off and you take f of the next number down, and so on and so forth, right? Does that make sense? And so you end up getting this thing that doesn't involve any f's, right? At the end of the day, you can compute f of 5 without using any f's. So the question is, figure out a way of writing this down without any f's in it. Okay, so there should be no f's on the right-hand side. No, it is. Yeah, Josefa, that's exactly what it is. And that is in this case for f of 5, that would be the closed form thing. But now I want you to do it for n, and that's just what we're going for there. Yeah, exactly, Christian. Okay, so does that make sense? Does this kind of clear up some stuff about numeracy 3b? Okay, so basically, so I was asked to kind of explain it again. So the problem is that anytime you want to compute f of a number, right? If I want to compute f of 100, well, I have to write that as 100 times f of 99, right? And then I have to compute f of 99, and then I have to compute f of 98, and so on and so forth. So what I want you to do is to tell me, is there a way of writing f? So we know that this is true, right? We're told that this is true. Now what I want you to do is tell me a way of writing this out such that there's no f's on the right-hand side, right? No f's over here. And yeah, exactly. Yeah. Yes, exactly, Curdy. Yeah. And now generalize that for n. What would it be in for n? Yeah. Yep, exactly. And that's the answer. No problem. Happy to help. Okay, anyone else? Anything else? Still got 10 minutes here. Mm-hmm. It's just multiplying the matrices without a, yes, exactly. Yeah. So in this example that I did right here, you're just multiplying these matrices, which would be the same as just multiplying these matrices. Exactly. So Jack, the numeracy questions are designed to set us up for the next section of the course. So no, you don't need to use matrices for either of the numeracy questions. Right, that's what the numeracy does. It sets us up for the next part of the course. No problem. See you too, Dora. Using only F in division, basically, like once you answer 2, I want you to use your answer from 2 to answer number 3. That's basically what I'm saying, Christian. Right? To write the expression in 3 as only your answer in 2 and division. Mm-hmm. Yep, Jeremiah. Well, not n though, right? You don't want n there. Yeah, no problem. See you, Josefa. Number 1, part 5, there's a red box over the 4. Oh, that's just, it's a hyperlink. So basically, if you click that number, it'll take you to question 4. Don't worry about it. Yeah. Yeah, that certainly seems reasonable. No problem. Okay, anyone else? Anything else? Because it seems that we've slowed down a bit here. Otherwise, we can call it a little bit early. Like, I don't mind. Night. For number 5, is it asking us to multiply it with a matrix A in number 4? Yes. Yeah. So in number 5, you are using the A that comes from number 4. Yeah. Can we use a closed expression from? Yes, yes, Brandon, I want you to use your expression from 3 to answer 2. Yeah, no problem. Night. Jack, yes, but I'm not certain what you meant by kept doing that versus just kind of like doing it at the end. Like you could just do it at the end instead, but like, yeah, that's okay. Yes, Sean. Yeah, you want the exact matrix which does this. But you can describe it in terms of I and J. So if you don't want to like write them all down, you can say, you know, U, I, C, or whichever one is part 1. S, I, J is this matrix for, and then describe it in terms of I and J, right? So you can either write down S12, S23, and S13 and write them all down explicitly, or you can describe what those matrices are in terms of I and J, because there's a very nice pattern that you can use in order to write that down. Perfect. You too. See you later. Have a good night. See you on Thursday. Okay, everyone. I think that we seem to be out of questions. So again, if you're just like maybe typing something, scream out or something so I don't leave. Otherwise, though, I think we can call it a night. And, you know, I'll see you Thursday. The recordings, they're in their usual place. Do you, have you never known where the recordings are? They're in, so if you go to meetings, you'll see that each lecture has a materials page. Oh, you know what? Let me send that to everyone just in case somebody else has that question too. There's a materials page. This is lecture 9104. So if you go to that page, that's where the recordings are posted, right? Just to make your life a little bit easier. But you don't want to have to remember this link, right? So in the meetings tab, it's the same place where you would find the Zoom info for this this Zoom session, and you'll notice that there's a link that says lecture 9104 materials, and that's where you would click to find the recordings. Okay, perfect. Okay, everyone, I'm going to take off. Thanks so much. Lots of great questions. Hopefully that helped you out. Have a good couple of days. Work hard on your assignment, and yeah, I'll see you all on Thursday. Okay, have a good night.